a couple of administrative things before we really get going. As hopefully you guys saw on Piazza, one has been posted. That'll be due basically a week and a half from today, so not this Thursday, but the following Thursday. First problem you should have been able to do sort of before you walked into the door, in this class, so certainly feel free to get started on that. Second problem, by the end of today, you should basically know everything you need to know. And then the third problem, which is kind of more simulation-based or really characterization of the sort of technology that you're going to be using in this class, you can actually probably already start doing, but some of the terms that I'll be using there probably won't be clear until at least probably the end of lecture on this Thursday or something like that. If you see some terminology that you're not familiar with, that's probably because we just haven't covered it yet. Other than that, as we sort of finalized last time, the discussions will be 2 p.m. on Fridays, just here in 540 AD Corey. This is obviously going to be held by Pierre Luigi. I called it a discussion. In reality, sort of half of the time will be office hours, half of the time will be discussion. Basically on the weeks where we've just handed out the homework, they'll kind of do a review of what the homework is all about, give you kind of critical information and all that. And then on the alternating week, they'll basically just make it office hours to answer questions that you guys may have. So without any questions on either logistics or class material from last time? Yeah?
Question on work. If we're using the HBISEC for the third column, it says use okay, and PFET, should we just, like the model that the website suggested as like NMOS and PMOS as the like model name, should we just use those? Or?
Yeah, okay. So the question was, basically in the homework it says, the exact homework write-up says something like, characterize NFET and PFET, and if you actually look at the models that are on the website, they're NMOS and PMOS. Indeed, just use NMOS and PMOS. People tend to use NFET and PFET and NMOS and PMOS somewhat interchangeably. So indeed, it's NMOS and PMOS that moves the name of the real model. Yeah, and Pierre Luigi, I think we'll cover some more sort of setup kinds of things this Friday, but all of that should be fairly straightforward. I think the quick start guide kind of gives you a pretty good hint on all of that. Okay, great. So unless there's other questions, let's actually go ahead and get back into the class material itself. So we were basically talking last time about passives, and I think we pretty much ended up sort of getting into some of the more detailed layout issues with resistors. So as you remember, we sort of spent some time talking about why with resistors, or actually more generally with any sort of analog layout, when you actually want to ensure matching, you really have to follow a so-called unit element-based approach, where pretty much literally any two things that you want to match have to be laid out absolutely exactly the same. Okay? So we spent some time talking about in the resistor case how, for example, the contacts could cause errors if you weren't careful about them. How, for example, even actually the direction of the current flow could cause some errors if you weren't careful about that. So I think basically at the very end we sort of started drawing what a so-called better unit element would be. And now let's just sort of redraw this again to make sure it's clear. Whereas an example, if I wanted to do some resistor unit element, then my sort of recommendation was to make it so that the unit element would always essentially actually built out of two unit elements, where essentially you make the connections as an example like this. So that essentially current is always flowing in both directions inside of the unit element. So that then once you take that unit element and you sort of put more and more of them together, you never have this problem of messing up the current flow direction. So as an example, if I take this unit element and then I start, let's say, repeating it, as an example, let's say I want to do something like one resistor that has value R and another resistor that has value 2R. I'm just going to draw sort of all the pieces that I'm going to need to do that. Okay, right? So remember, basically, each one of these things is an individual unit element. And then to construct an array, or rather, let's say one resistor with value R and another resistor with value 2R, the way you basically do that would be something like the following. Right? So you basically have, you take that upper element, you connect it in series with that bottom element, and that would come out from there. This other element here, and I'll just do this in a different color, just so there's no sort of confusion. The two sort of terminals would be coming in from there. Right? So this would basically be R, and then essentially from, let's call this plus, and let's call that minus, that would be 2R. Right? Does this make sense to everybody? Or? And again, notice the whole trick here is that I did it in a way that now, I'm basically guaranteed that all the current flows directions work out because every single unit element has both directions anyways. Okay? Now, there's one other thing that we talked about last time, which is if I looked actually at the environments around these individual unit elements, in this picture that I've drawn here, it's not really exactly right, because notice, for example, this unit element in the middle has something above it and something below it, whereas the unit elements on the top or on the bottom only have another unit element that's similar to them either above or below them. So in reality, what you actually have to do is add these so-called dummies. So that's actually shown in this picture here as well, where here I'm going back to sort of the simpler unit element with everything in just one direction, but pretend I could actually expand it to do a better job with that. You'll notice that I actually added these so-called dummies that aren't really actually doing anything, except just to try and make sure that the local environment around each individual unit element really is exactly the same. Okay? Does this make sense to everybody? Or? Okay, so now there's one other sort of, let's say, important technique that has, at least it gained a lot of attention in the past, which is a so-called common centroid. Okay, so it turns out that in almost any manufacturing process that you deal with, but particularly with silicon ICs, there's some sort of spatial gradient. So what I mean by that is that, if you looked at, for example, the thickness of the poly on one corner of the die or one corner of the wafer, and you compared it against the thickness of the poly on the other corner of the wafer, you'd usually see some sort of distribution that, was varying across the wafer. So as an example, you might get some like either Boeing shape, or you might have like a linear gradient, or so on and so forth, where you have maybe thin on one side and thick on the other. Okay? So as you remember, we said that in analog it was all about matching the relative values of things. Well, if I've got a spatial gradient, then even if I do a really, really good job with just sort of nominally making things look very similar, then that gradient could actually also cause errors in the values that you actually would get. Okay? So actually, long ways back, people thought of a lot of very clever techniques to deal with this. And basically, the most effective one to deal with this gradient issue is a so-called common centroid. Okay? So the idea is that if something is varying, in this case at least linearly over space, if I make it so that basically each element that I'm interested in sort of samples the variation in that space, let's say uniformly, then I can make it so that on the net all those variations will cancel. Now, that's kind of a complex way of saying something that actually turns out to be very simple. It basically just says that if you have a bunch of unit elements, you want to make it so that sort of the effective center, or the center of mass of each of those elements, is always in the center of your whole array. Okay? So let's just look at that by a sort of simple example. So let's say I had some gradient that was going in this sort of arbitrary angle that I've shown you this way. And let's say that it was a linear gradient, so that as you walked kind of on planes like this, you had some variation in the resistance. Let's say some variation in the width or something like that. Okay? Now, you'll notice that the way these things are drawn, they're totally symmetric along the x-axis, right? So whatever component of variation there is in the x direction, that one, just by nature of the way the resistors are drawn, that would actually automatically work out, right? Because even if I had something that was thin there and wider there, they would all have that same shape, right? So they'd all match each other from that standpoint. So now the only thing we really have to take care of is this gradient in the vertical direction, okay? So that's where this so-called common centroid trick comes into the picture. So notice, by putting one unit element for the 2R resistor there and the other one there, sort of below the center point or symmetrically around the center point of the whole array, then now indeed if I just have this linear gradient, then if I call this sort of being my nominal resistance value, and let's say that that gradient either causes a plus delta R, or in this case a minus delta R, then if I tie these two resistors, or unit elements really in series with each other, that gradient will basically cancel out, right? Because as an example in this case, let's just pretend that for whatever reason the resistor was a little bit narrower on this upper piece. Well, if the gradient really is linear, then because I've placed everything symmetrically around the middle point of the whole array, then however much this one is, let's say, thinner, this one would be thicker by the exact same amount, or wider by the same amount, and the variations there would cancel. Okay? Does this kind of make sense to everybody? Or? All right, so it turns out people used to spend a lot of time doing exactly these kinds of layouts. But to be honest, these days, it's used much more rarely. Now, does anyone have an idea why that might be? Why is this sort of not quite as popular as it used to be?
Maybe larger wafers, so each die has like a smaller gradient.
Okay, you basically said that there's larger wafers than there used to be, and so each die has a smaller gradient. I basically would kind of agree with that, yeah.
More restrictive design rules?
Okay, you said there's more restricted design rules. That's also actually potentially true as well. But I think the answer is actually a little bit simpler in the following sense. So basically, all of this scaling stuff was about improving the density, right? So if you think about it, we're packing, whatever, 30, 100, 100,000, 1,000 times more transistors in the same physical space as we used to be. So if you kind of think about it, if I really had very large gradients across, the same physical area as I used to have, then pretty much guaranteed nothing would really work, right? So in other words, indeed, the fabrication technology has gotten a lot better about essentially controlling those gradients. And maybe to say it another way, if you're doing things right, the area of your circuits also tends to be much, much smaller in a more modern technology versus in one of these older technologies. So that for sort of the same functionality you were looking at, now you're in a much smaller physical space. And so just, if you're in a smaller physical space, the net effect of the gradient should also be smaller. So what I kind of said is actually, I think, the synthesis of what both of you guys, and probably what other people were saying as well. It's really just saying that basically, most of the circuits are small enough, and the gradients are typically small enough, that this usually isn't a first-order consideration. Now, having said that, if you really do some ultra-high precision stuff, with really, really large unit elements, really, really large arrays of elements, then you really do have to start thinking about some of these common centroid types of layouts. By the way, I would claim that it's actually kind of really good news that you don't have to worry too much about common centroid. Anybody have an idea why that is? What's kind of annoying about common centroid?
Routing?
Well, okay, the routing is actually annoying, but maybe even from a simpler way of saying it, I did this for sort of a simple thing with 2 elements, right? And I basically made it in a way that I only had to worry about the vertical gradient. You can imagine if I have a big 2D array of stuff, right? And I have lots and lots of different elements that I want to match each other, it can start to be a pain in the butt to actually figure out how to do that layout very, very quickly. And indeed, the routing and everything else can also become a pretty big mess, okay? So, as I said, this is a good thing to know about because you may indeed have to use it. But the good news is that for most of the designs you're doing, as long as you follow the rules of sort of, keeping the local environments the same, watching out for current directions, making sure you use appropriate unit elements, for most of the stuff you'll do, you'll actually get more than good enough matching. Okay, so if we think some more about sort of, resistor layouts, there's actually even a whole lot more kind of very detailed things you can start getting into. So just as an example, if you want like a really large value of resistance, you typically don't want to do that as, like a contact there, and, some line that would be microscopic on this drawing, going off like with this really long skinny kind of wire like that. Typically, it's much more convenient to actually just do things with a more reasonable aspect ratio, right? So as an example, you may do that by this serpentine kind of layout, right? Where rather than just having it snake, or rather than having it run completely in one dimension, you just snake it so that you're sort of fitting into a more compact 2D space. Does that make sense to everybody? Or? Yeah.
Is that sort of thing actually typically done in FET? Normally you can actually like trim your poly around corners.
Okay. So it depends on, let's say, what technology you're in. There are some technologies where you wouldn't even actually be allowed to run a polyline vertically versus horizontally. They would all actually have to be in the same direction. But nobody says this has to be poly per se, right? This could be metal, this could be something else. Even if it is actually poly, you could actually put, another via or contact there and run the vertical thing in metal. The basic point is more just to say that, if you have really, really large values or really, really large unit elements, you'll tend to probably snake them rather than have this one long, linear kind of thing. It turns out there's actually even more, let's say, interesting effects you can get into, where, for example, in particular, if you're using, poly or diffusion-based resistors, it turns out they're actually thermoelectrics. So if there's even like a temperature gradient that resistor experiences, you'd actually see some either basically errors in matching, or in fact even, it might act as like a thermoelectric generator. Okay? So there are some more clever layouts you can come up with based on this kind of snaked thing that's, let's say, symmetrically around the center point that would actually cancel some of those effects. I'm not going to spend a lot of time sort of talking about these kinds of things, but again, if you're really going to be doing some very high precision kind of matched layouts, it's actually worth investing in this book here. that basically tells you about all the tips and tricks that people have built up over the years to exactly deal with these very, very, let's say, particular and sometimes tricky issues you can potentially run into. So again, if you really, really have to do some really, really high precision stuff, worth taking a look at some of the issues people have run into in the past, so that you're not actually making the same mistake that's been done many, many times before. Okay, so we spent a lot of time sort of talking about layout and essentially sort of quote-unquote real or normal resistors. But turns out sometimes you just want resistors that are so big that it's kind of impractical to do it even with something like an unsolicited poly or diffusion resistor. So in that context, it turns out that actually transistors can be rather useful. Okay, and the basic idea hopefully is pretty obvious. If you wanted to get a resistor, but again, you want it to be very large value, then you can instead basically just take a transistor, and by setting the appropriate gate to source voltage, you can basically control what the resistance really is. And again, hopefully the idea here is fairly obvious in that, if you took a transistor and you biased it with a high enough VGS, that basically it's looking like it's in the triode or linear region, such that, of course, the channel charge is basically relatively flat underneath there. Indeed, it looks essentially just like a resistance, right? So if I look at sort of the resistance across these two terminals, you can get sort of one of these classic types of equations here, which really just says that, it's a resistor with some dependence upon what the VGS minus VT actually is, okay? So I'm not going to spend a lot of time on, any of these equations, because again, I think you've seen many of them before, and as actually we'll get into fairly soon, the equations are kind of bogus anyways, but they just tell you a little bit about sort of potentially how you could use this thing as a resistor. So the other thing that I will mention here is that, even though transistors can be sort of reasonably useful to get large resistors, the problem with them is that they vary horrendously. Okay? So like if before we said that something like a polyresistor was, I don't know, plus minus 20%, something like that, MOS transistor or MOS resistors could easily be plus minus 100%, if not even plus minus thousands of percent, okay, depending upon where exactly you bias the thing. So the question you may ask here is, well, okay, so fine, maybe it lets me get sort of a large resistance in a relatively small area, but where is this actually useful, right? Where can I actually use some resistor that I don't really even know what the heck the value is going to be to any, even to within, let's say, an order of magnitude? Where might that be still a useful thing to have? Nobody can come up with even a single circuit that, you just want a big resistor.
You control it in feedback, for example.
Okay, so I guess you paid attention to me last time when I said that feedback was almost always the answer. You could indeed control it in some sort of feedback. That's absolutely correct. That's one thing. But let's say I'm really lazy. I just want something really simple. But are there any cases where I just want a really big resistor and I don't care that much what the exact value is?
Like pull up or pull down resistors?
Pull up or pull down resistors in what context?
I mean, I guess like at the input of something, like so that you can, like if you don't have anything connected to it, it's still going to be some value.
Okay, so you said something like, this could be at the input of something where maybe you didn't have anything else connected to it. There's actually one very specific case that is indeed very common that would do that, so I'm just going to go to the front to get some more.
Send the open loop gain of
Okay, so you said setting the open loop gain of an op-amp. That's possible. That's probably not the first place I would do it, but that's possible.
Providing a DC bias?
Yeah, there we go. You said providing a DC bias. So let's just say, from whatever reason, I need to AC couple into the input of my amplifier, which in this case, I'm indicating the amplifier just by a transistor, right? Well, I need some resistor there to basically set that DC bias. So what's the only things, or the only things I should say, that I really care about from the standpoint of that resistor? In other words, what sets the value that I would want to use there?
the RC time.
Yeah, okay, so first of all, the value of that resistance would set the RC time constant. And there, as an example, if the resistor was much bigger than it was supposed to be, what would happen? What was that? Yeah, basically, it's really actually the zero that would move to a lower frequency, right? which means you'd be passing things at a lower frequency than you were before. Now, in many cases, you probably don't care, right? So as an example, if it was, let's say, I don't know, let's make something up, 10 kilohertz instead of 100 kilohertz, as long as all of my signal stuff is way above that frequency anyways, I may not care all that much, right? What's the only other thing you actually care about in terms of the value of that resistor? So let's say, indeed, you don't care too much what the what the pole that's set by that is, the zero set by that is. What else might you care about in terms of that resistor?
Well, that actual bias voltage.
Okay, you may care about the actual bias voltage. In this particular context, what does that mean? What does that say about sort of the value of this resistance? This is a little bit of a trick question, by the way.
Something with the gate current is 0.
Ah, okay, so you said nothing if the gate current is 0. So, is the gate current 0? Ah, okay, so you said it should be, and somebody else said it's small. So now I'm going to be, let's be really precise, and let's be actually specific. So I'll give you guys a hint. In a 90 nanometer CMOS technology, that gate oxide thickness is somewhere on the order of a nanometer. So is the gate current precisely 0? Okay, a bunch of you guys are shaking your heads, so I guess a bunch of you do indeed believe in quantum mechanics. And the answer is indeed that current is probably not really 0. Okay? Because when you get that thin of an oxide, electrons can literally just tunnel directly from the gate into either the channel, to the source, to the drain, and indeed, you will see non-zero currents flowing through that gate there. Okay? So the only reason I brought this up, by the way, is A, because this is an interesting effect we'll talk about a little bit later on in the class, but B, in this particular context, it just says you want to make sure that that resistor that you use there is small enough that you don't have any problem with the leakage current basically destroying the DC bias you're trying to set there. Okay? But again, to the extent that, even if this thing varies by a factor of 10, as long as that current is, let's say, 10 or 100x higher than what the leakage current would have been, you're basically fine, right? So again, this is another example where even if it's really highly variable, you just want something that's basically big in terms of its value, but within a very small physical area. Just because it actually happens to be sort of, on the slide here. Any other places you guys can think of where you might be okay with this kind of resistor?
MOSFET C filters?
Okay, well, yes, you can indeed read. That's good. MOSFET C. So, what do you think it's actually doing in the MOSFET C filter? What purpose is it serving? Any thoughts? Okay, well, so actually we'll talk a whole lot more about this later, but basically that resistor there is probably just setting some kind of time constant that, again, has to be low enough, but once it's low enough, you don't really care what it is. Okay? That's probably the most reasonable thing there. There's actually another one, which, if you can read the second line there, is something you might be able to guess at. So where else might you be okay with using this kind of resistor? I should say the second bullet point, to be precise.
Very large value resistors.
Okay, used inside of what? Sorry, and the particular bullet I was referring to was that one. Yeah?
You should use it inside of like a current source.
Okay, that's possible, although current source might be a little bit tricky. But let's maybe I'll ask you guys a different question. So what kind of references did you guys hear about in the past? What kind of references did you guys talk about in, for example, 140? I thought I heard somebody say it.
Yeah, band gap.
Band gap references. Okay, so what is the sort of output of what's the units of the output of a band gap reference? Typically. Yeah, it's a voltage, right? It gives you a voltage that is directly set by the band gap voltage. Okay, so inside of those band gap circuits, you usually need some kind of resistor. Do you care all that much what the value of that resistor is? No, you don't, right? Because as long as things are kind of in a reasonable range, you'll still get the band gap voltage at the output. Okay? So indeed, these are just a few examples of places where even though the value can vary all over the place, you just want something big and you don't actually care all that much about what the precise value really is. So with that, just to sort of maybe quickly summarize a little bit in terms of resistors before we start moving on to talk about capacitors. Kind of a couple of the key points were that we said that, remember, in a sort of standard digital CMOS process, they really want to make those resistors go away as much as possible. So oftentimes, if you really want to get in the analog domain a large and precise resistor, it's going to take you quite a bit of area, at least compared to what the MOSFETs would have been. And even then, there's still going to be a lot of non-idealities. So run-to-run variations, they're going to have temperature coefficients, voltage coefficients, and so on and so forth. So kind of the take-home message is that in many sort of cases, you're going to try and avoid those resistors whenever you can. Okay? There's actually some very specific examples that were developed very heavily here at Berkeley, particularly these so-called switch capacitor types of topologies that were developed exactly to try and avoid some of the badnesses associated with resistors. So especially if you can avoid them in sort of so-called critical areas like amplifier feedback networks, electronic filters. It says here A to D converters. I'll say a little bit more sort of what that means later on down the class. Basically, if indeed you can avoid using resistors, that tends to be sort of a good thing to do, at least within a certain set of applications. And as I said before, we'll kind of get back to that point. So we spent a lot of time talking about resistors, but the other sort of main element, in fact, probably the element you'll spend most of your time worrying about, particularly in this class, but in general in analog design, is actually capacitors. Okay? So let's again sort of think about our IC process and think about how we could actually build a capacitor. Okay? So this is kind of the simplest example that I can think of. I just take a piece of metal, right? I've got my substrate underneath it, and I basically say, well, hey, I've got a parallel plate capacitance between that piece of metal and the substrate. So that seems, indeed that's a capacitor. But I claim there's actually a fairly big problem with this particular way of building a capacitor. So what's the problem with building this capacitor? And I'll see if I can get somebody else besides you. If not, I'll come back to you. Yeah?
Well, you can't really change the voltage on your substrate.
Yeah, exactly, right? The substrate is the substrate, unless I happen to be lucky and have multiple wells in the process or whatever. That substrate is supposed to be tied to ground, right? So how does this limit you from a circuit standpoint? As an example, what's something you cannot do with this kind of capacitor? Yeah, exactly. You can't do exactly this AC coupling picture that we drew before, right? Because one side of the capacitor has to be ground, right? So in some cases, maybe that's okay. There's actually some specific applications where that's actually totally fine. But in general, if we want to build a capacitor, we'd like to be able to basically bias either one of those terminals to something that's not necessarily just ground. Okay? So indeed, we can try and fix that. We've got a process with, let's say, 7 metal layers. So I can always just go and take one of those other layers, put it on top of the first one, and now indeed I've got capacitance between those two layers. Right? And now I can indeed independently bias, let's call this top, let's call this bottom or bot. Now indeed I can actually independently bias those two. So this still works, but I'd claim still has some problems. So the first question is, let's say indeed I was to take this, this real physical thing that I built here, and I was going to try and build a model for it in SPICE. Okay? So let's just call this, I don't know, C main. Okay? So in SPICE, ideally speaking, of course, I'd have this top terminal, I'd have this bottom terminal, and I'd have some C main there. Okay? So is my SPICE model done, or do I have to add some stuff? Yeah?
You have a cap on top of the substrate and also bottom.
Yeah, exactly. I've actually also got capacitance from top to the substrate. And physically, that's just coming about from essentially the fringe field coming off the side over there. And let's just call this, I don't know, CT. Now, I've of course also got capacitance coming from the bottom to the substrate. Right? And that one could be both due to the fringe here, let's call it CB1, CB2, as well as due to the parallel plate on the bottom right there. Okay? So let's just call that CB1 plus CB2. Okay? So indeed, the problem here is that I don't really just have one capacitor. I've actually got the main capacitance that I really wanted, plus these extra parasitics. Okay? Now, just to be clear, which one of these parasitics between CB and CT, meaning the parasitic from the bottom plate versus the parasitic from the top plate. In the particular example, which one of those two do you think is worse? Meaning higher.
Bottom plate.
Yeah, bottom plate, right? Because it's got not only just this fringe, it's actually also got that parallel plate. And even worse than that, it's closer to the substrate than the top plate actually is. Okay? So because of that, people often refer to these basically fixed parasitics that are connected to the substrate that you can't really control. Oftentimes we'll refer to that as a so-called bottom plate parasitic. It turns out in reality, oftentimes there's no difference between the so-called top plate and the bottom plate. It's just that because they sort of have this picture in the back of their minds, the term bottom plate really caught on, and so if you hear that, you should always think that there's actually parasitics on both sides of the capacitor, but sometimes indeed the bottom side is worse than the top side. Okay? Now, it turns out there's actually something you could do to potentially improve this picture somewhat. Specifically from the standpoint of this bottom plate issue or this parasitic issue that we just talked about. So can anybody think of a small modification we can make to this layout? And I'll come back to you in 1 second if I don't get, Come on, we got to get some new people raising their hands here. Yes?
If you lift the bottom plate, then you'll decrease the capacitance between the bottom plate and substrate while at the same time increasing the relative capacitance of the metal plates.
Okay. So you said a few things in there, all of which were correct. But we're going to come back to, I'll ask you maybe some more questions as to what you actually can do and what you can't do. So what you said was that, hey, well, in this picture, there's kind of a couple things that in principle I should be able to do, right? So one is, if I could increase that distance from the substrate to the bottom layer, I'd have less parasitics, right? The second thing you said was that if I could actually reduce the distance between those two capacitors, that would also be good for two reasons, right? One is it would pull me potentially farther away from the substrate. And second is, and more importantly maybe, it would actually increase the capacitance that I really wanted, right? That main capacitance would actually go up. So everything you said is in principle true. Now, from the standpoint of you as an IC designer, what do you actually get to control? Do you actually get to control this spacing? Yeah, generally not, right? Usually that's just kind of set by the fab, right? They say, well, the spacing is whatever the spacing is, take it or leave it, okay? How about that distance there?
Yes.
Okay, so there's actually two ways you can answer it. So you said yes. Why did you say yes?
Because you have more than 2 metal layers.
Okay, so great. So you said, I actually have more than 2 metal layers, so I can actually choose a different metal layer to try and get myself farther away from the substrate. Now, once you've chosen a metal layer, you're stuck, right? You can't do anything. You get what you get from the fab. But indeed, if you chose a higher metal layer, potentially you could actually get a lower parasitic. Okay? Okay, there's actually one more thing, there's one more trick you can kind of play, which is somewhat more subtle. And I'm guessing you already know the answer, so I'm going to see if somebody else can come up with it. We'll come back to you if not. Yeah.
Is it possible to put like a different material between the two metal plates? Like if you put polyester in a different electric process?
Oh, I see. Okay, so we'll talk about this actually in 1 second. You basically said, if I can increase the dielectric constant in between those two capacitors, that would be good, right? That would actually increase my main capacitance. Or equivalently, for the same sort of size of main capacitance, would give me a smaller bottom plate parasitic. Now, unfortunately, again, that's kind of set by the process. So by design, I may not be able to do that. So let's see if Andrew.
Oh, that was what I was going to do.
Oh, that's what you're thinking. Oh, okay. So there's even one more.
Maybe you can put a vertical.
Okay. So actually, I'm going to talk about that. You said I might be able to rotate this whole structure to be actually vertical rather than horizontal. That will indeed actually have some interesting characteristics. We'll come back to exactly that question. There's one last sort of. This is somewhat of a classical trick, but maybe you guys haven't heard of this before. But there is one last thing that we can actually do. Yeah.
You can also use multiple metal layers on top of each other. And then
Absolutely correct. Again, we'll come back to that one. But for now, I want to stick with basically just these 2 metal layers. And the modification I actually want to make is below them. So what do you typically build inside of the substrate? N-well. So indeed, let's put an N-well here. What can I do with that N-well now? Is there any clever trick I can play? Why is it useful to have an N-well?
You can tie that to a mall cap. Like,
You said, let me see if, I think what you said is probably correct. We'll come back to it. Go ahead,
Yeah,
Seth.
you can control the voltage so that if you keep it at the same as the bottom plate, you get rid of that parasitic.
Okay. So that is indeed one very clever idea. You could basically make a connection to that end well, and then say, well, I'm going to somehow magically connect this to the bottom terminal. Okay? Now, here's where things get a little bit interesting. If I literally just shorted it to the bottom terminal, what would happen? Or rather, is that necessarily a good thing? Yeah, right. So remember, anytime you've got a P and an N, there's always a junction there, right? So that means there's always going to be this depletion region. Of course, assuming you've kept things reverse biased as they're supposed to be, right? And so that means that now, okay, maybe I got rid of this capacitance from the bottom of the metal to the top of the substrate, but instead I've replaced it with capacitance from that junction, right? Now that could indeed be a good thing. Depends upon the spacings, the relative doping levels, and things like that. But actually, if we take this just one small step further, I claim we can actually do even better than this. Okay? And the way you do even better than this is basically the following. Instead of tying that to the bottom, let me tie it to just some bias voltage. But let me do that through a really big resistor. Okay? So can anybody tell sort of what's the trick I'm trying to play here? And by the way, that bias voltage, I'm going to tell you, is going to make the N side much, much higher than the P side. In other words, I'm going to be applying a strong reverse bias to the diode. Yeah?
If you can deplete the N well, then it's not conducting.
Well, okay. Oh, wow. You're very aggressive. So you said if I can completely deplete the N well, then I won't have any conduction at all, and I'll have a very, very small parasitic capacitance. That's actually true. Typically, the N wells are sort of thick enough that you can't exactly do that, but it's a very similar idea.
So you increase the depletion region, which is the capacitance. The capacitance gets larger and it's in series with the
Capacitance gets smaller, you mean, but yes.
yes.
Yeah, so you basically said exactly what I was going after. So if I apply a really big bias right there, indeed what will happen is I will increase the width of that depletion region. That will make the capacitance associated with that region get smaller, right? Now, if I've done things quote-unquote right, and this is now why I needed this big resistor here, what I'm really trying to do is I'm trying to make it so that this capacitor here shows up in series with that junction capacitance, right? Not only that, I'm trying to make this junction capacitance as small as I can by basically biasing the heck out of that diode, okay? So the reason I needed this resistor was so that I can actually apply that bias, but do it in a way that doesn't cause you to just basically create an electrical connection directly to that node, which would mean you just directly get that bottom plate capacitance there. Okay? Yes?
Is that better than just putting like a shallow trench below it or something?
Okay, so the question is that better than just putting a shallow trench or something below it? And the answer is it kind of depends. And it depends on something very simple. If you can put a trench underneath here, and that trench is basically deeper than the depletion region you can get from here, then the trench would be better. However, if this depletion region is actually wider than what you can get from that trench, you'd actually prefer to do this. Is that clear? It's an excellent question. Now, by the way, you may not always be able to really put that shallow trench there. There's certain rules you have to follow, but that's the sort of zero-order answer. Does this make sense to everybody? Or? Okay, so we spent quite a bit of sort of time thinking of this very simple structure. It turns out that's actually going to be quite useful, because a lot of the considerations we talked about there will show up in the other types of capacitors as well. But much like we did with resistors, this is just kind of a table showing you what are the different possibilities in terms of how to implement capacitors. Ranging from something sort of very similar to what we showed, so the sort of called metal-metal capacitor, metal-to-substrate capacitor, metal-poly. Sometimes we even have a so-called poly-to-poly capacitance, where they actually will play some of the tricks that you guys talked about. They'll make a thin layer of oxide or a thin layer of insulation between the two pieces of poly to try and get a higher capacitance density. But actually, as you'll notice here, by far the highest density of capacitor you can get is a so-called gate capacitance, meaning you just take a transistor and hook it up as a capacitor. Okay, and I'll just sort of show one example of how you might do that. So let's say you just took an NMOS transistor, you shorted the source and the drain together, and you just called that, for example, plus, and this, for example, minus. Okay? So you notice this density is at least like something around 10x or so higher than all of the other numbers that are shown there. Why is that the case? Or was there a question in the back?
Yeah, why is MIMCAPS not listed?
Okay, so MIM I will talk about in 1 second. You could sort of, there's a version of MIM which is basically metal-metal, but obviously it's just with a thinner insulator. And we'll come back to that in 1 second. So I guess DJ was maybe going to answer the question. Why is the gate the really dense capacitor there? Yeah, the oxide is thin, right? We just said a second ago that was like a 1-point-something nanometer oxide. And trust me, that's way, way thinner than any of the other oxides that are in the entire rest of the chip. Okay, so simply because of that, that's typically the highest density capacitance you can get. Now, by the way, just as maybe, again, thinking a little bit outside the box, let's say you really needed really, really big capacitors. Is it a good idea to take just a sea of transistors and cover your whole chip in, gate poly like that, or might there be a problem? Okay, there's indeed this leakage thing that we talked about. That's very true. The specific issue I'm thinking of is actually directly related to that leakage.
You can short the positive.
Yeah, so remember this is a tiny little thin oxide, right? All it takes is a couple molecules of error, and you'll actually get a short. Okay, or all it takes is some small little defect in the oxide, and I could very easily get a short between those two terminals. Okay, so oftentimes from a yield standpoint, they will tell you, look, you can't have more than a certain percentage of poly density, just because if you have more than that, it's unlikely that you'll get any chips that actually yield. Okay, that's just another thing to be a little bit careful about from that standpoint. Okay, so let's just sort of look at a couple of these capacitors in more detail. So first, again, if we just look at the MOS capacitor, where again, all we're really doing is just tying the transistor up, approximately speaking, something like that. Okay. So I'm assuming you guys have sort of seen this MOS CV curve many, many times. Actually, who has seen this at least, 5 times or so? Okay, well, so again, the key sort of idea here is just that as you get close to essentially the threshold of the transistor, there's actually a depletion region underneath, and so the net capacitance you get is relatively small. But as long as you stay sort of well away from the threshold, meaning you DC bias it either, in this case for an NMOS, with a large VGS or with a very negative VGS, then largely speaking you'll get a much more flat or well-behaved capacitor there. Now having said that, there is indeed going to be a lot of nonlinearity in the capacitor, especially if you're anywhere sort of close to that region of operation. There's indeed going to be a temperature coefficient because the threshold has a temperature variation on it, so that would also cause variation in the capacitance itself. But nonetheless, just like with sort of the MOS resistor, this is still actually quite useful in many applications. Okay, because there's many cases where you can actually guarantee that indeed there will be a good DC bias on that capacitor, such that it'll actually stay in the relatively flat region of operation there. Okay, so I mentioned here sort of a Miller compensation capacitance. Again, you just sort of know where the gate and the drain are relative to each other, so you can actually use a MOS transistor for that. And another very common one is a so-called bypass capacitor, or a decoupling capacitor, where the idea there is that if you look in the chip, you've got your VDD rail, you've got your VSS or ground rail, and you need to put some capacitance onto the chip itself just to make sure that if there's any variations in the current, you try and keep that voltage as constant as possible. And here in this particular context, something like a MOS capacitor really is quite useful because basically that supply voltage, you know which way it's biased, it's relatively fixed, so indeed you can try and guarantee that the capacitor always remains either an inversion or an accumulation. Does this make sense to everybody? Or? Okay, great. Okay, now I want to spend a little bit of time just talking about capacitor layout, because it turns out that if you thought resistors were tricky, capacitors are probably actually even a little bit worse. So everything I said about the resistors basically applies to capacitors as well. But there's a few additional things that we really have to think a little bit about. So I'm showing you here, and actually probably the best way to understand those is kind of by looking at this picture of an example layout that someone has done, which turns out to actually be a pretty good layout. Okay? So first, before we sort of dive into the details there, let me just ask you guys a little bit of a brain teaser, and maybe I'll just describe exactly what's happening here. So everything that's kind of shaded in like that, just pretend that that's one layer of metal, and essentially these lines around it is kind of like another layer of metal underneath. Okay? So each one of these things is basically a unit element that's trying to create a certain value of capacitor. Okay? And if you sort of see lines running in between, that means you're actually connecting those unit elements, typically speaking, either, basically in this case, in parallel. Okay? So before we sort of get into exactly what's going on with this layout, can anybody tell what is the sort of ratio of the two capacitors that I'm trying to build here? And by the way, there really are only two capacitors. They're just built out of unit elements. Yeah, it's 7 to 2. Okay, so basically these two unit elements here are basically tied together. Okay, so you can see like this top plate is tied to that top plate there, and the bottom plate is tied right there. So those two unit elements are basically tied in parallel. And it's a little bit hard to see, but basically if you sort of follow around this ring right here, as well as internally on the top plate, you'll see that those 7 unit elements are also tied in parallel. So this is indeed a 2 to 7 ratio. Now, if you look kind of carefully at this unit element, you'll see there's some really initially weird looking stuff inside of there. So you'll notice like they all have these like stub thingies hanging off on the sides of the top plates right there. Anybody have an idea why those stubs are there? Yeah.
Well, you need to connect the like 7 units together, but you don't want to have like unbalanced stubs in them, so you just all.
Okay, yeah, so basically what she said was that I have to make connections between either the 7 unit elements or the 2 unit elements, right? And in some of those unit elements, that connection is going to be made or not, right? So the reason I'm going to include these stubs is that if, as an example, let's say I just looked at kind of this outer edge over here, right? So let's say that, yeah, I connected there, and then I connected here. As an example, on this other, let's actually look over here in the center right there. Right, as I keep going up on this, maybe I keep making a connection there, but then, hey, all of a sudden, I have to make a connection to the left, right? Well, if I didn't put a stub basically on the left of this capacitor, then all of a sudden, the 2 unit elements are different, right? Because here, this capacitor has something going to the left, this capacitor has something going up, and remember I said it has to be exactly the same? This is indeed the level of paranoia you have to have when I say exactly. Okay? Because left versus vertical, not necessarily the same. Okay? In fact, in some of the modern technologies, even the rules for doing layouts on vertical versus horizontal lines could be different. Okay? So again, what was actually done here was just really trying to make sure that, even when you think about how you connected the things together, the parasitic capacitance or the total capacitance would actually match between those things. Okay? Now, with capacitors, things get even a little bit more tricky, because you may not care just about capacitance between those 2 plates. You might even actually care about parasitics between the different capacitors, right? Because that's also capacitance. In some sense, that's even worse than resistors, because with resistors, unless there's an electrical connection there, you're not going to have sort of the stray resistance. Whereas with capacitance, any 2 things that are kind of close to each other are going to have stray capacitance between them. Okay? So again, you have to be really, really careful about thinking about how all those sort of edge and fringing effects may affect the final sort of capacitor matching you really care about. Does this make sense to people, or? Okay. So this is now coming back to Andrew's question. So in some processes, you'll get what's called a MIM capacitor. MIM just stands for metal, insulator, metal. But this is typically a sort of add-on option, meaning you have to pay some dollars to actually get it in your process. Okay? So the idea here is that what you're paying for to get from that is just a capacitor that gives you higher density than you otherwise would have gotten. And so the way these things are typically built is, if you looked at, for example, 2 metal lines on the original chip, let's say that had some certain amount of spacing between them. Well, what this MIM capacitor basically gives you the option to do is essentially take something on that same metal layer, but bring it in closer to the layer, as an example, typically below it. And also you'll typically use some kind of high K dielectric in between them. Okay? Or if not, just bring them closer to get a higher capacitance density. Okay? So again, the idea here is just that with a thinner oxide there, or a thinner dielectric, perhaps a higher dielectric constant, you can get a higher capacitance per unit area, and also typically better sort of parasitic types of characteristics. These things used to be fairly popular, so that if you're doing any sort of analog stuff, you basically get this MIM capacitor option. But these days, it's actually sort of nowhere near, it's actually pretty rare to see this option really used. And the reason for that is that now we actually have a lot of metal layers in our chip anyways. And as we'll discuss in 1 second, we can actually use those metal layers to build very dense, very sort of effective capacitors simply out of what already exists in the process. In other words, without having to pay any additional cost or dollars to the foundry. Okay? So the way you would actually do that, and by the way, these capacitors that just use sort of the existing metals, are often what's called MOM capacitors, or MOM capacitors. Don't ask me why MOM capacitor, that, by the way, that stands for metal oxide metal. So don't ask me why that's really all that different than a metal insulator metal, because the insulator is usually an oxide too, but this is just the terminology. Okay, so if somebody says MIM, that's like, costly, expensive, bad. Somebody says MOM, that's like, okay, it's standard, exists anyways, don't worry about it. Okay? So if we think about just taking the metal layers that exist in our process already, there's kind of two, at least in principle, two simple ways we can think of as to how to build that capacitor. The first is actually this example that we looked at right from the beginning. We basically said, well, hey, we could take one layer of metal, kind of pour that horizontally, then take a second layer of metal, pour that also horizontally on top of it, and then just rely on the parallel plate capacitance in the vertical direction there between those two horizontal plates of metal, right? The other way we can do it, which I believe actually Jethro suggested earlier, was we can kind of flip this whole picture on its side, right? What we can basically do is we can say, well, hey, why don't we take some piece of metal, kind of have it sit vertically like this, and then as close to it as we can, place another piece of metal that also sits vertically like that, and largely speaking, rely on the parallel plate capacitance between those two, okay? So, when I drew this picture, I was actually being a little bit, I shouldn't say fake, but the relative aspect ratios here maybe are not exactly correct. And to really understand that, let's maybe sort of start thinking about exactly what the trade-offs between these two are. So let's say I'm thinking about this horizontal parallel plate here. What is it that you can indeed control? And what is it that's basically fixed by the foundry? Yeah?
The dielectric thickness is fixed by the foundry.
Yeah, so the dielectric thickness here, the dielectric material, totally fixed by the foundry, right? But what is it that you can actually control? Yeah, you can basically change the width and the length of these structures, right? So you can kind of make these arbitrarily big, right? Okay, how about in this vertical geometry here? What is it you can actually control, and what is it you can't? And by the way, just to keep things simple for now, let's assume we're going to do everything with, in this particular example, just one layer of metal. So what is it you can actually control, and what is it you can't?
Just length is the only thing you can control.
Sorry, just say that again?
The length is the only thing you can control.
Okay, that's kind of basically correct. So you said, in some senses, the only thing I can really control is the length, right? Now, that's not exactly accurate, but what you're saying is very true in the sense of once I do a little bit of optimization. So if I wanted to, what things could I potentially control?
Spacing?
Yeah, okay, so I could potentially control this spacing here, right? I could also potentially control the width of that line there, right? Because the width and the length, that's still kind of in the layout dimension, right? The spacing I could indeed also actually, in principle, control. Now you said really the only thing you can control is the length, and I actually kind of agree with you. So why did you say that?
DRC rules.
Okay, specifically what about the DRC rules?
You only can have the metal lines so close together and so narrow.
Right, so what you said was you can only make the metal lines so close together and so narrow. Now, why do you want them to be very close together, and why do you want them to be very narrow?
Higher cap and higher density.
Yeah, right, so the closer I make them together to each other, that's like the distance between the two plates, right? The smaller I make that, the higher cap I get. similarly with the width of those lines, right? If you kind of think about it, making that line wider, the only thing it'll do is increase the cap to what's below it, right? But that's not really the cap I'm trying to get. I'm just trying to get the cap to the neighboring line, right? So indeed, if you really sort of, ideally speaking, if you could do all the optimization you wanted to, you'd make the thing as narrow as you possibly can, set by the DRC rules, and spaced together as close as you can, again, set by the DRC rules. So now, given that exact discussion, and now I'm going to make everybody participate here one way or another, we're going to have to decide if you had to build the densest, lowest parasitic capacitor that you could in a modern technology, who would use the horizontal version? One brave soul. Who would use the vertical version? And by the way, horizontal is this, and vertical is that. So who would use the vertical version? Ah, okay. So the vast majority of you got the quote-unquote right answer. Now you have to answer why, though. So why would you use the vertical version? What's good about the vertical version?
It seems denser for the same amount of cap, and you can control even though you can't directly control the thickness, you can add metal layers and connect them with vias.
Okay, so you're absolutely right. You can add metal layers. You said it seems denser. It turns out that's probably going to be correct, but I claim we haven't given you, you haven't quite given me the information needed yet to explain why it probably will be denser. And by the way, the reason is a little bit, again, you have to think a little bit outside the box about who really controls the process.
The layer-to-layer thickness is probably going to be much more than the minimum spacing you can get for
horizontally between. Okay, so you said that this layer-to-layer thickness is probably going to be much larger than the spacing that you can get here. And I would kind of tend to agree, but why?
Well, the processors are mainly made for digital guys, and they want less interconnect cap.
Yeah, right? So it's not even just that, but just to repeat for the camera, it's exactly the fact that, remember, the process is usually built for the digital guys, right? What's the number one thing digital guys care about? Well, okay, it is true, from a certain standpoint, I agree with its capacitance, but, again, taking one level up, what's Moore's Law all about? Okay, yeah, so a bunch of you guys said this sort of convex combination of what I'm getting at. Remember, it's cost, right? How do you drive down cost? You make the darn chip smaller for the same function. How do you make the chip smaller? You get more transistors per unit area. You get more wires per unit area, right? Well, how do you get more wires per unit area? You make the darn width of the wires smaller, and you make the spacing between the wires also as small as you can possibly make it. So in other words, what this is basically getting at is that the digital process guys have a really strong motivation to make that spacing and that width as small as they can possibly make it, because that's good for them. Whereas, in terms of this thickness here, that spacing between the layers, turns out that is actually going to be fairly small, but from the digital guys' standpoint, if they could, they would make it as thick as possible, right? In fact, it even turns out they'll start playing games where they'll screw around with the dielectric properties of the so-called intralayer dielectric versus the interlayer dielectric. And again, in many cases, to the extent that they could, they would be totally happy to make the basic capacitance between the layers, for all intents and purposes, 0, right? Because, hey, it doesn't buy them anything, right? It's just extra cap, nothing else is useful there. Okay, now, there's processing reasons why you can't actually do that, but nonetheless, the point is that the digital process drives you towards wanting to use these vertical types of designs. Now, as we mentioned before, and you'll see this in 1 second, for these vertical designs, you probably won't do it really with just one metal layer. You can actually leverage the fact you have many metal layers and kind of like fill these things vertically with vias and metal layer, via metal layer, and so on and so forth. Again, we'll sort of see a picture of that shortly. But the meta point there is indeed that this tends to be the more attractive option in more advanced processes. Now, I've talked about all of this as if there really is only vertical or horizontal. In reality, you can actually make some mix between the two. And if you look at the homework, you'll see that indeed there's certain cases or certain types of designs where you may want to make those kinds of optimizations. I've also sort of drawn this as just sort of the simplest possible example of the patterns you can draw. You can actually do some much more sophisticated kind of things. It turns out that actually some folks down from Caltech about 10 years ago or so, I believe, proved that the optimal density you could possibly get was by drawing some fractal patterns. Don't worry, I don't think anybody really actually does that, but it's interesting to know nonetheless. But bottom line is that indeed, there's actually some optimizations you can do here to really get the best possible capacitance density. Okay, so again, these are the so-called MOM capacitors. The way these are typically built, specifically given that it's these sort of vertical types of designs that are typically most attractive, is essentially you sort of have these fingers that you run, and then as you can kind of maybe see here, you stack multiple metal layers on top of each other. And then you just have one sort of piece of metal line at either end to kind of make the connection of the complete, let's say, bottom plate versus top plate. And again, you're really utilizing the horizontal fields between the lines to form that capacitor. So now actually this is again something you'll see in your homework, but just to make sure everyone's kind of paying attention, with this kind of structure, when we talk about top versus bottom plate, do you expect one to be larger than the other?
Yes.
Do you?
No.
No, right? Because if you kind of look at it, if I labeled this top and I labeled this bottom, there's kind of no difference, right? If I looked at it from the vertical standpoint, how much of that area is over the substrate? Basically, it's totally symmetric, right? So this is again one of those examples where top and bottom don't really necessarily make sense in the context of there's not really a big difference between the two. But nonetheless, people will still typically refer to this as bottom plate parasitics. Yes?
The one thing about that picture is, like, you have it laid out, everything's uniform between bottom and top layer. But in process, your design will say that the higher you go, the bigger your metal lines have to be and bigger spacing. So what do these capacitors end up actually looking like?
Okay, so actually, that's a very good question. The question was, I drew everything here as if all the metal layers were completely uniform. And typically, as you go to the higher metal layers, the thickness and minimum spacing you have to use is larger than at the lower layers. I don't have an exact picture of that, but this picture that I'm drawing here may help to answer that particular question. So if we take this same structure and kind of basically slice it right along here and then turn it on its side, so kind of look at the side view of the whole wafer, it would typically look something like this, right? So you basically have a metal line, a via, a metal line, a via, and so on and so forth. And that's how you sort of build up this full vertical structure. Now, in the instance you were talking about, what that would basically mean is that rather than, for example, this top piece looking like that, it would have to look, for example, like this. Okay? Now, the question there obviously becomes, well, what does the sort of so-called unit cell really look like? Right? Because I have a couple of options there, right? I could either make all of the lower layers the same width and the same pitch as that upper layer, right? Or I have to try and come up with some way of kind of matching those lower layers with those upper layers. Okay, and that's actually a question that was asked in one of the previous year's homeworks. So I maybe won't give you the exact answer here on tape, so to speak. But from 10,000 feet, typically what you end up wanting to do, or typically the answer is, if these upper layers really have substantially worse pitch and width, usually you just don't use them. Okay, because basically the overhead, the amount of extra capacitance you get versus the extra sort of design effort and all that, usually is just not worth it. Okay? Does that kind of make sense? Or?
Yeah.
Okay.
Doesn't that also give you a trade-off, though? Like, your min caps are always on usually the top layers, where, you want to have your routing on bottom layer, but if your caps are on your bottom layer, your routing has to be, somewhere else.
Yeah, so remember, typically speaking, you're not going to get min caps, or, unless you really explicitly ask for them. But there are indeed many trade-offs with these kinds of designs in that, if I really wanted the highest possible density, I'm going to use kind of all of the reasonable metal layers that I can, right? That obviously means no other routing or anything else can go anywhere through that space, right? But in most IC designs, what will really end up happening is indeed you'll use as many of these layers as kind of practical, and then you'll do all of the sort of global routing on top of it. And you may actually build the sort of cap unit cell so that the real signal routing basically is kind of inherently built into the capacitor itself. Again, we'll maybe see some specific examples of that later on, but that's the general principle. Okay? So as we discussed before, obviously, the more metal layers I give you, the thicker those metal layers are for the same sort of minimum width and spacing. the more capacitance density you're going to get. Now, having said that, there are some cases which you really care about is not necessarily just the capacitance density itself, but actually the ratio of that capacitance to the bottom plate parasitics. Okay? So as we said before, the only way, and I said bottom plate parasitics, I should be careful, I mean really all of the fixed parasitics, meaning the parasitics going to the substrate. Okay? So as we said before, one very effective means of reducing that parasitic is basically just trying to move the capacitor farther away from the substrate. Okay? So in this context, what would that actually mean? What's your only, let's say I took a capacitor that nominally used all of the metal layers. What's the only thing I can do to basically move it away from the substrate? Yeah, I basically just have to chop off some of the bottom layers, right? So now here's the interesting question. If I chop off this bottom layer, does that guarantee that for the same total value of capacitance that I really wanted, am I guaranteed to get a lower relative fixed parasitic or not? No, right? Why not? What's the trade-off? Yeah, so basically the density I get per unit area, because I chopped off those bottom layers, is lower, right? So the question is, what hurts more? Does it hurt more to lose that density? Or is it better to actually basically have a thicker spacing away from the substrate? And obviously, depending upon what the actual values there are, you may not know a priori which one of those two is the right answer. And again, this is actually a homework problem that you may get asked, or an exam problem or something like that you may get asked at some point. Okay? Maybe just one final note on these before we move on is that it turns out these types of capacitors, because digital guys, again, are really highly motivated to get these very thin lines with very small spacing between them, they tend to actually have very reasonable accuracy as well as matching. So order sort of maybe 10, 20% or so accuracy, and matching easily on the order of 1.1% or so. And again, it's just the only reason that happens is because the digital guys are also very motivated to keep that well under control for their own purposes. Okay? Okay, so just maybe really quickly I'll mention a couple of additional things we're going to have to keep in mind, specifically with capacitors, but more generally for all of our passive elements. If you guys remember that, when we talked about resistors, we said that anytime I built a resistor, especially in the sort of IC technology, I always also got some capacitance. Right? So for example, in those diffusion resistors, I had some extra capacitance from the junctions. Right? Well, similarly, if you build a capacitor, whether you like it or not, you're also going to have some resistance inside of that capacitor. Okay? And in particular, what that means is that even though we like to think of a capacitor as just being a capacitor, oftentimes there's going to be these so-called distributed effects where things you do on one side of the capacitor won't necessarily immediately affect the other side of the capacitor. Okay? So that can cause all kinds of, let's say, fun analyses and things like that you might have to do. We won't spend a ton of time on that. In fact, you could even actually get not just parasitic resistance, you can have some parasitic inductance. But the good news is, for most of the dimensions we're talking about, most of the frequencies we're talking about, that inductance is kind of small enough that it wouldn't have a big effect on the overall impedance. But, resistance inside of the cap, or vice versa, capacitance with a resistance, definitely can be a big deal. Okay? So let's actually go back to our example of a resistor. But this time, let's say that anytime, just as a simple model, anytime you draw a resistance, it's also actually going to have some capacitance associated with it. Okay? So as we had said already last time, if this is the case, then that means that obviously beyond some frequency, I won't really get the impedance I wanted from that resistor. Instead, my impedance will be dominated by this capacitor. Okay? Now it turns out there's another sort of directly design-related implication of this, which is that if we actually look at what would happen is, let's just say again we took a poly resistor, and I'll draw the top view now. Right, so let's say I had a poly resistor, one of them that looks like this, and then we draw just a second one that will kind of overlap in a different color. So the second one that basically was the same thing, just wider. Okay? Well, if you sort of think about it, this blue version inside of there, right, for the same physical length, has more squares of resistance, right? Not only that, if I think about the parasitic capacitance that's underneath that structure, there's a smaller total area from that blue thing, right? So I have less capacitance, right, for the same physical area. So what that basically tells you is if I compare against this blue version and the red version, which is wider, is going to basically have more parasitic capacitance for the same resistance, right? In other words, if I looked at this plot here and I just compared essentially, the impedance versus frequency of those two designs, right? One of them would start to sort of, let's say, roll off at, say, I don't know, a gigahertz or something like that. Whereas the other one, with the wider value, for the same nominal value of resistance, would actually, drop to half of its nominal value at that same frequency, okay, in terms of the impedance. And again, the reason for that is just very simple. For the same physical resistance, you actually will now have more parasitic capacitance, okay? So what does this say about sort of, how you'd like to build your resistors? How should you sort of choose this width, especially if you're interested in, the high frequency performance of that resistor?
Skinny.
Yeah, you want to make it as skinny as you can, right? Now, what sometimes stops you from doing that? Yeah, okay, the current capacity. Okay, so just to give, let's say a somewhat exaggerated example, let's say you're really aggressive. You say, you know what? I'm going to take my gate poly, right, which in our process we said was like 90 nanometers. And I'm going to use that for all of my resistors. And let's say that, in this particular thing that you're trying to do, you have to push 2 milliamps through that poly. What's that poly going to look like after, I don't know, an hour, 2 hours, maybe 5 minutes, something like that?
What poly?
Yeah, what poly? Okay, that's actually the best answer I heard. I heard melted, I heard, electromigration. What poly, right? The thing is just going to explode, right? There won't be any poly left there. Okay, so sometimes indeed what you have to do is you have to use a wider resistance, like wider in the layout, simply because of the current you're trying to handle. Okay? So this is actually, kind of a general thing to keep in mind is that anytime you sort of deal with large currents, that tends to mean you need larger physical elements, which tend to have lower, larger capacitances associated with them, which tends to mean you need more currents, which, obviously gets into a nice positive feedback loop. Okay? So again, keep those things in mind because indeed you'd like to make the resistors as small as you possibly can, but sometimes just because of the physical current you're shoving through it, you're not actually allowed to do that, and you will indeed pay a penalty in terms of the parasitics. Okay? So, I also mentioned here that, of course, if you really want to get a sort of very accurate frequency response, you may need some sort of distributed model, but oftentimes actually even just a sort of simple pi model like this will really do the trick. Okay, so another sort of important thing to mention is that because of the fact that you're always going to get some finite resistance inside of your capacitors, that means that basically you obviously not only have these sort of distributed effects that I was talking about a second ago, but the so-called Q, or the quality factor of the capacitor, is also going to be limited by that resistance. Now, it turns out there's some sort of interesting physical things that happen where, as an example, if I take an AC bias voltage and I apply it across sort of a capacitor like this, then what you'd actually, and actually be careful, you actually would apply it like this, okay? What you'd actually see is that if you looked at the sort of current distribution along this horizontal direction, you'd see it would not actually be uniform, okay? What you'd actually see is that you have a lot more current basically flowing through the pieces that are kind of close to the source than you really have flowing through the pieces that are at the end. Okay, and the simple reason for that, hopefully, is fairly obvious from the circuit. Right? Basically, you have all these sort of internal loops that you're going to be flowing through, and the closer you are actually to the source, the more basically current you're carrying from all of the other branches in the rest of the circuit. Okay, now, I don't mention this because I expect you guys to run any EM simulations or anything like that, but even if we're not worried about these specific distributed effects, it does imply that if you're really worried about basically the quality factor or the parasitic resistance of your capacitors, there are some, let's say, interesting tricks that you can play. And one in particular, specifically for these capacitors, is that I can basically contact both sides of the capacitor, and based on that actually reduce the parasitic resistance by a factor of 4. Okay? Now, because this is not always immediately obvious as to how this magic factor of 4 happened, let's maybe sort of draw a simple picture to motivate where that might have come from. So let's just sort of draw the top view of this capacitor, right? So I just have sort of a piece of metal, right? So as we all know, that piece of metal for a given length and a given width will essentially have some resistance getting from this side to this side, right? Oh, okay, so now if I connect a source on one side, but I connect the same source on the other side, what's kind of like the worst resistance that either one of those sources would actually see, like individually? What's like the worst case resistance you can sort of think of? And let's just, by the way, say that originally with the L and W, you had a resistance of R. So, yeah, it's half of that, right? Because basically this source has to go from there, this source has to go from there. So if I kind of draw a line in the middle, each one of them basically has half of the original resistance. Okay? So now that got me one factor of 2 here. Where's the other factor of 2 coming from? Yeah, they're in parallel, right? I have 2 resistors, each of R over 2, in parallel, right? So by the way, all we said before was that effectively the length became half of the length. So that got us to R over 2. And then if we just put 2 of those resistors in parallel, which is indeed what we're doing, then now actually we have 1/4 of the resistance we originally had. Okay? So now here's maybe the, again, thing to think about. What's the hack that I'm playing here? Or what's the thing that maybe is not so straightforward to do, even though this indeed would get you a factor of 4 reduction in the resistance of the capacitor itself? And I'll maybe give you a hint. Let's pretend this thing is really, really big. So like, this is one edge of the chip and this is the other edge of the chip. What's the cheat that I'm using here?
Well, it's got to be hard to get your signal with both sides, like with the same phase and everything.
Yeah, exactly, right? So when I drew this, I assumed the signal was exactly the same on both sides of the capacitor. Somehow magically it just arrived there and there's no difference between them, right? That's exactly the sort of cheat that's being played here. Now, in maybe the example that I gave, that was kind of a little bit of an exaggeration, right? I said I had to go from one side of the chip to the other. Maybe getting the signal on both sides of the chip is a bit of a pain. But actually there's some clever sort of physical layout tricks that people can play that makes that perhaps not as bad as it quite sounds. But indeed, you have to always sort of keep this in mind of anytime somebody gives you a trick that sounds really good, there is indeed usually some other price you're paying for it just in a different place. So as usual, you have to evaluate what costs you more, right? This double contact thing, by the way, is actually fairly common inside of transistors. And the reason why it's actually useful there is that oftentimes, specifically with sort of transistor capacitors, one of the biggest resistances that you get is just through the very thin pieces of poly at the gate. So there, even if you have to route an additional piece of metal on top of it to connect to both sides of that poly, it could actually be worth it simply because the metal resistance is so much lower compared to the poly resistance. So getting that factor of 4 in the poly really does buy you quite a bit. Does this make sense to people, or? Oh, don't worry too much about what this thing on the upper right. It's just sort of saying what's the sort of current distribution across the capacitor versus the physical distance. And it's just saying something similar to what we said before, which is things that are close to the contact have more current. Things that are sort of farthest away from the contact have least current. Don't worry too much about this. It's not critical for the particular point we're making here. Okay. So maybe just as a last and quick note to wrap up on the stuff we've been talking about so far, obviously we've spent a lot of time on resistors and capacitors, but you may be wondering, well, what about inductors? Okay? And as I mentioned before, mostly speaking in analog mixed signal design, we typically don't use inductors very often, for actually maybe 2 simple reasons. One is they're just usually really big compared to the circuits we're interested in. And 2, perhaps maybe even more importantly, they're kind of a pain in the butt to model. Okay, so we spent a lot of time talking about kind of these resistors and capacitors, all the detailed, intricate things that can happen, but inductors in many ways are sort of even worse than that. Okay, because you have to know the exact current flow path and things like that to really get these right. Now, having said that, even in the sort of quote-unquote analog applications we're talking about, there are occasionally times where we'll actually use these kinds of inductors. Okay? And probably the most common application, at least in sort of wideband kinds of systems, is the so-called shunt peaking technique. Okay? So, by the way, how many of you guys have heard of shunt peaking before? Just raise your hand. Oh, only a few of you. Okay, so the basic idea is the following. So let's say I take this amplifier that I just drew in red on the left, and I compare it against this very similar amplifier that has this inductor added into it. Okay? Turns out this idea of shunt peaking is that if I really choose the value of this inductor appropriately, for the exact same bias current in this amplifier as in this amplifier, I can in principle at least make the bandwidth of this amplifier approximately up to about 85% or so higher than this amplifier. And again, for the exact same power dissipation. Okay? So the way this works is actually kind of interesting. Okay, so roughly speaking, to understand this, the way you should sort of think about bandwidth is that bandwidth is really about how fast you can move charge in and out of a capacitor, right? Well, if you think about this structure here, right, what's going to happen is that, let's say I put some, let's say some step signal into the gate right there. Well, basically, two things are going to happen. I'm going to start pulling current out of that capacitor, but I'm also going to start pulling current out of that resistor, right? So initially, right when the transition happens, I'll probably be mostly pulling out of the current out of the capacitor. But right away, I'll also start pulling current out of the resistor, right? And the more current I pull out of the resistor, the less charge is coming off the capacitor, right? Well, if you think about what this inductor does, right? With inductors, the whole trick is they don't like to change their current instantaneously, right? So what actually happened is, by placing that inductor there and again choosing just the right value for it, I'm actually going to force, at least initially, all of the current to come out of the capacitor. Okay? And again, to the extent that I have more charge per unit time coming out of the capacitor, at least initially, that indeed means I have effectively higher bandwidth than I otherwise would have. Okay? Now eventually, obviously, the inductor kicks in and you have to get current flowing through there as well. But that's where the sort of, let's say, trick comes in terms of choosing the right value there so that it actually gives you this benefit that you're looking for. Okay? The only other reason that I mentioned this shunt peaking here is that this is one particular application where a lot of the badnesses of inductors are maybe not quite so horrible. Because usually the big problem with IC inductors is that you don't really just get an inductor, you actually get a resistor too. And oftentimes that resistor is kind of really big compared to what you'd like it to be. Well, the good thing with these shunt peaking applications is that you can actually tolerate a pretty big resistor there. You're not really shooting for a very high quality factor out of the inductor. You're really just trying to use it for the sort of speed up effect that I just described. Okay? Now, having said all that, we won't spend really any more time on shunt peaking in the rest of this class, simply because there's lots of other implications from doing it. So as an example, your frequency response typically is not flat. As an example, if you look at the regular design and compare, if that's, let's say, I'll label the axes, let's say that's the magnitude of your transfer function versus frequency. If you compared that against the shunt peak design, that will typically look something like this. Okay, so it won't really be flat. That, again, has other implications in terms of the performance or behavior of the rest of the system. Okay? But nonetheless, it's a good thing to just sort of have in the back of your head because there are some applications where indeed you may want to be able to play these tricks just to get that last, 50, 60% of bandwidth improvement. And if you have to, you can actually indeed build inductors on IC processes. You basically just sort of wind things up in spirals, or sometimes in multi-layer structures that look sort of like toroids or solenoids. These are actually, again, used quite widely in RF circuits. But you have to be careful because the values you can really get out of these things practically are typically limited to around 10 to 20 nanometers or so. We'll typically use sort of the top metal layers, unlike with the capacitors we talked about earlier, because there you really need the thickness of the metal just to reduce the resistivity of the coil. Okay, so any last sort of quick questions for today? Okay, great. So if not, I'll see you guys on Thursday. We'll pick back up with the lecture that I have.